Hello, everybody, and thanks for attending this talk by Professor Ricardo Baeza on big data, machine learning, and justice. Today, in fact, this talk is part of 2 cycles of seminars. On one side, it is the third of 5 seminars on fairness, accountability, transparency, and ethics, FATE, which are organized by the department under the Maria de Maeztu strategic program during this spring. Within these seminars, we want to address, from a humanities and ethical perspective, the increasing impact that ICT is having in our human lives. And we are programming a seminar each week. If you arrive earlier, a reminder that the next week, I mean, we had the program here. There's another seminar next week and in 15 days. And within this topic today, Professor Baeza is going to address some of the main challenges of using big data and machine learning, and in particular, how machine learning can apply to justice with its pros and its cons. On the other side, today's talk is also part of the integrative research seminars in which faculties from our department present their research in easy, accessible ways to colleagues and students and PhDs and researchers from completely different areas. So let me introduce, although we all know Professor Baeza, let me introduce him. I mean, because he's a historical member of the department, which he joined in 2004. He's the founder of the Web Science and Social Computing team, a research group. And also, we don't have the chance to see him as often as we would like, because he's always traveling abroad or in California. He's definitely one of the great ambassadors of our department and of the UPF in general. In fact, he's indeed the most cited scholar from the whole UPF, and the third in Spain in computer science, in whole Spain. He has been an ICREA professor. Between 2006 and 2016, he was vice president of Yahoo Research Labs, first in Barcelona and later in Sunnyvale in California. Since 2016, he's the CTO of Intent, a search technology company based in California also. He's an ACM fellow, an IEEE fellow. He has received many awards, of which I will just mention the 2 of the last ones, which was the Premio Nacional de Informática Ángela Robles, that was last year, some months ago in 2018, and very recently the Premio Salva y Campillo in 2019. So I think I could spend the whole talk talking about his CVs and achievements, but I think it's time to pass the floor to Professor Baeza. Thank you very much.
Thank you, Sergi, for the introduction. I wanted a shorter introduction, but here we are. So this is a mixture of things that I have done research about and things that are in my interest, and also a compilation of things that we should worry about. So this is the agenda. So basically, I will go very fast about some big data and machine learning. I will assume that you know all of that. Depends on the audience. That's a bit different. I will have one slide about asking the right questions when you do data science. Almost nothing about opportunities. I think you can read about them every day in the news. But then I want to go into the challenges in more detail. And although I have a case study applied to justice, we can use justice also in another way, is justice in machine learning, so the opposite. And I will talk a bit more about that when I talk about bias. And then I have the last part, which is more like what is the impact of society and some important things that may happen in the near future. Please, if you have questions in the way, feel free to stop me, because I will talk about many different topics. So let's start with the problem that big data poses. And this is inspired in a talk I saw last year by Claudia Perlich. And let's say we have this graph. This graph has a complexity of the problem in the y-axis and the size of the data in the x-axis. And let's say I have to build a machine learning model just to distinguish my picture from anyone else. And this is not so difficult. So you need a few pictures from me, let's say 4, and many others from other people, and you can get a very good classifier that basically will translate a picture in either Ricardo or something else. The first thing is important here is that there's no intelligence here. So we just changed an image representation to a text representation. And although many people will try to say that that's intelligence, it's just a translation. Because when the model does that, the model doesn't really know who I am, how complex I am, and so on. So it doesn't have any idea on the real complexity of the problem. But the complexity of changing just the representation is not that difficult. Now we can take something like a famous Einstein's equation, like energy is the mass of the object times c squared, where c is the speed of light. And this is a big data formula. In what sense? Well, it applies to any object in the universe. So basically applies to all possible objects, but of course the complexity is trivial because it was already solved by Einstein. So we didn't need to come up with the formula. It was given to us. Let's say now that we want to predict the stock market. Doesn't matter where. Let's say Wall Street, which will be the most difficult one. Well, this is a very complex problem. And the truth is, it doesn't matter how much data we get, will still be a complex problem because it's close to random. I mean, people is not rational when they invest, although some people may like to believe the opposite. Otherwise, we will always be there doing models for Wall Street. And if that happens, Wall Street will not exist because then it will be too easy to predict. And finally, we can get to something really complex where we need more data. I hope you know this, one of my favorite paintings, The Garden of the Lights. Well, let's say you need to build a model that will recognize every animal in that picture and any other picture that is similar to that one. Well, you need more data to train that well because the animals are not exactly how they should be. So this is the space of problems that we are looking at. And then in big data, we have many ways to basically differentiate all the different dimensions, but this is one that became popular. It's the 5 Vs and works amazingly. It's the same in Spanish, so, and I don't know, maybe in Catalan, so it works. And I added 3 other dimensions that I think are important to build this matrix. So which are the problems with the data, which are the problems with computing with the data, and which are the problems that affect us as humans. And I will not read this whole matrix, but I will really focus on the things in red. For example, there are many issues in the data, like redundancy and bias and privacy. Only one in computing, scalability, and briefly. I think most of the technical ones are not that difficult because they are technical and we are working on these things. And the last column is about people, and of course, again, bias and ethics, I guess, are the main points here. And that's why this is part of this FATE series of seminars. Okay, so one single slide about machine learning. So this is nothing new, and the main 3 reasons we are having this today, because we have more data, we have more processing power, GPUs, although GPUs were not designed for machine learning, the main users of GPUs today is machine learning. And deep learning, neural networks, nothing new, but now we can use them because we have more machine power and we have more data. And there are many applications. I will not read them, and I'm sure I don't need to explain how, say, a deep learning model works or any standard supervised learning model. So we'll assume that you know this, and you can check many, many books for this. Now, what are the opportunities? Well, we want to have data-driven decisions. And many times data doesn't really predict what we think about it. we find things that are completely unpredictable, and that's the interesting part. We can do global optimization, so not only local optimization. We can not only learn, we can predict, and more important, we can prescribe, so act before things happen. We can use our personal data. In the future, maybe all our health will be in our mobile phone, and all the models will run there to basically keep your privacy, and maybe we'll have a lot of zero-knowledge proofs with other actors about ourselves and the rest of the world. We will have machines deciding for us. The famous ADM of, for example, GDPR, and I will get back to that. But you need to ask the right questions. And these are some of the questions that we need to ask every time we look at big data, machine learning, and data science. Things like what data we need, not what data we have, which is a different thing. How much is really big data? I will get back to that because most of the time it's not big data. How we collect it, how we store and transfer it. Then we need to understand the data, how sparse is the data, how much noise, how much redundancy, biases, spam, outliers, and I will focus on this part on the talk. Then when we go to analyzing the data, then we need to look at privacy. Do we have to anonymize the data or not? How well our algorithms will scale? I will talk about scalability. Can we visualize our results so we understand better what is happening? And we need to remember this, which is should be obvious, but sometimes people don't remember it, is that the quality of an algorithm is bounded by the quality of the data that uses. So basically, as many people say in English, garbage in, garbage out. Doesn't matter how good is your algorithm. So let's start with the challenges. And I will let you read the joke. I do this in internet quite often because I don't want to be predicted, so I need to lie. But this happens in every political survey today, because finally the surveys don't really say the truth. And one problem here is that we know a lot and we talk a lot about successes on, let's say, big data, but we don't know most of the failures. And of course, the failures is at least 1,000 times more the number of successes. And this is one problem. We don't talk about what went wrong. We only talk about what went well. And sometimes those things are not replicable. So the first challenge is scalability. And I guess I will do only one slide to gain some time. But the first line should be obvious. If you double the data, in the best case, you will double the time because you need to read the data. And in most cases, it will be much worse than that. So one class of algorithms that I have done some research, but not too many people is looking at, which I think is important, is that we should look at the trade-off between the time complexity and the result, the quality of the result. And here is a real example. For example, detecting named entities, a typical task in natural language processing, in linear time and very good quality. And then if you can do it in linear time, then you can process more data. And if you can process more data, you can find more entities, although it's not the optimal quality, but still you can find more. So what happens is the following. Let's say we have quality here in the y-axis, and let's say we have the size of the data here. And let's say this is the best algorithm so far. This was published in the best conference, and is the current winner using deep learning. Let's say A1. So if you look at this graph, and you compare A1 and A2, you will say, okay, we should use A1 because A1 is the best quality. However, this graph is not showing the whole truth because time is not involved. Usually you have quality and data size, but time is not there. Let's say that this algorithm A1 can process this amount of data in the time t star, But A2 can process much more data in the time t star. And this point is when A2 becomes better than A1 in quality. So basically, you can trade quality by putting more data. Let's say one case you find 85% of the entities, in the other case you find 80% of the entities, but if you basically can process more data, you will find more entities at the end. So this is the N star, where if you give them the same time, then A2 becomes better than A1, because in absolute numbers, it's better, because it can process more data. And I think we need more examples like this, because I think there are plenty of more where you can lose quality, but you can recover quality by basically using more data in the training phase or in the processing phase. So the second challenge is noise and spam. And well, noise comes from many places. For example, could be from the sensors that measure things. And that would be a completely different topic, but imagine that there's a failure in one sensor, and this sensor was built in millions, and there is a failure in all the sensors. Well, sensors are not like people. They will fail all the time. And if all of them fail, how we will know that they're failing if they're all answering the same? So I don't know how people will solve this problem in the future, but it will be much worse than dealing with human data. Spam is a very particular class of noise. Is when there is data that basically is there to deceive you. And basically you have some bad actors in the system, and that happens in the web often. For example, false pages, false links, even false clicks that are basically to deceive search engines and other people. Well, the typical way to fight against spam and also noise is what is called the wisdom of crowds. So basically when the majority is right. That doesn't even work in democracy, so I don't know if it works here. We hope so. But for example, it's really the wisdom of all of us. And I will get back to this, because the truth is that it's not the wisdom of crowds, because not all people do the same. Third challenge, and this will be the longest one, because I think it's the main challenge that combines all the things we have mentioned before, is redundancy and bias. So for example, data dependencies. That will be an implicit redundancy. Or could be explicit redundancy. How much data is duplicated? Is duplicated because it has to be duplicated, or is because the process duplicates it? For example, if you look at the web, about 25% of the data is duplicated, say mirror sites and other things. But the semantic duplication is much larger, and I will get back to that later in the talk. The next question is, are there any biases? So how many people look for bias before analyzing the data? Well, and there are many. And it's not only data bias, which is the most important, but there are many others that are important I want to mention here, like activity bias, algorithmic bias, and interaction bias. Now, when I say algorithmic bias here, is basically bias that comes from the algorithm itself, not from the data. Basically, the algorithm is doing something wrong and is adding something new. Well, the first sample, the first class is data bias, and we can show like thousands of cases. Let me give you the first one related to justice, as we will touch this topic later. And the typical examples are from the US. Here is from the UK. So this is the criminal justice system in England and Wales in 2014. So the first row is the population, the second the arrest, then the prosecutions, the convictions, and finally the people that end in jail, in prison. So you can see that if you're white, the probabilities go smaller. If you're Asian, doesn't change much. If you're black, will multiply almost by 4. So basically the system will help to take you to prison. And then it's very easy to learn this from data. And I will get back to this later when we go to the use case of justice. Gender bias in translation. So anyone from Turkey here? No, no one? Okay, good. So I write, he's a babysitter, she's a doctor. I use Google Translate. I'm sure you have done this. You can try it. We get the Turkish translation. I assume this is correct. I cut and paste this on the left side. I translate it back, and I get, she's a babysitter, he's a doctor. Magic. Well, in Turkish, there are no genders for pronouns. So basically, there's no gender in the Turkish variant. And then, when you translate back, you get the most frequent translation. Recently, in Twitter appeared a discussion about a paper that shows how easily you can learn gender biases sentences. And although the paper said that was not the case, and then it's not clear because they made a mistake and they were not replicating the exact previous work of the authors. So it's, even when analyzing bias, there is no clear agreement in this. Let me give you another example. This is from Eduardo, one of my PhD students here at the UPF. It was published a bit more than 3 years ago. And this is the fraction of biographies of women in Wikipedia. So you see that from 1600 to, let's say, end of the 90s, things have been improving. There are more women in Wikipedia compared to men. It's still not half, it's only 24%. And interesting, there was something important at the end of the 18th century. So I guess it's the French Revolution. Things change. But then you may say, well, there's nothing new here. This is just systemic bias. The truth is that there is a worse thing happening here than systemic bias, and will be obvious after I show you the answer. But sometimes bias are not obvious until you know them. So what is the main bias here? The main bias is that most editors in Wikipedia are men. For example, for biographies, only 11% of the editors that give their gender are women. That's another problem. It's not compulsory to give your gender, and many women don't give their gender to avoid any harassment. And then maybe that number is, say, 15%, but it's still 15% is very far away from 50%. Here we have another question that depends on every country. Is more social question will be, do women have the same opportunity to become Wikipedia editors? So it's not only who can write, it's only who has the opportunity to write. So we need more women in Wikipedia. Another bias comes from us. So us as a group. Most people, they just watch. Let's take the web as a best example of it. So active users are less than 10%. Doesn't matter which platform you take. Of course, the exact number only is known by every platform. So with Diego, another one of my PhD students here in the UPF, asked the question of how many users produce most of the content. So it's the democracy of the content. Let's say, how many users produce 50 plus epsilon% of the content, half the content. And here are the results. We look at 4 data sets. Facebook was small, Amazon reviews was large, Twitter was very large, and Wikipedia was also large. And for example, in a small sample of Facebook, we found that 7% of the people wrote half of the post. In the case of Amazon reviews, a collection you can find at Stanford, which is large, we found that 4% of the people wrote half of the reviews. So when you look at Amazon, be careful. So when I look at this, it cannot be possible. I mean, 4% of the people writing half of the reviews and they're not getting paid? Well, I don't know if they read the paper, but 1 month later, Amazon started a campaign against fake reviewers. And then, a bit more than 2 years ago, they kept this campaign because there were a lot of fake reviews. Even some people have done models on how many fake reviews you need to put to get better sales. There's an interesting paper by IBM Research on that, on modeling the impact of fake reviews. So here we look at the quality of the content, and using something that's called the text entropy, we found a positive correlation between the entropy of the text and the number of stars in the reviews. You can put certain number of stars. So if we look at the best reviews, then we found that 2.5% of the people wrote half of the best reviews, which is even more biased. So that even shows clearly that someone is paying them. Well, we look at Twitter. Twitter, there is a place in Germany that has all the Twitter data from 2011 for research purposes, and we were able to run our algorithms on that collection, and we found that 2% of the people posted half of the tweets. No one is paying them. There's a very easy explanation. It's called ego. There are some precedents that cannot avoid it. And then, in all the usage of Wikipedia, we found that 2,000 people, which is 0.04% of the editors of Wikipedia, wrote half of the initial English Wikipedia. And they were paid, of course. They were paid by the Wikimedia Foundation. And perhaps thanks to them, we have Wikipedia today, because no one will basically contribute to something that is empty, right? You need to see like the glass half full, at least. All the time people will look at the glass half empty, so it depends on the person. With Diego also, we look at the problem that I was interested in, and I think it's interesting to mention it here, is what I call the digital desert. The digital desert is all the content in the web that no one ever sees. So it's a real long tail of the content. And we found here, if looking at Wikipedia data, is that if you take all the articles that were modified or added in 1 month, then 31% of them were not looked at the next month. So this is an upper bound. Maybe 30% of the content of the web, if you take a time segment, no one is looking at. And looking at the Twitter data, we found that 1.1% of the people that basically tweets don't have any followers. So I don't know if I understand how Twitter works. But this is like to go into the Sahara Desert and scream. It's it's a cathartic experience, but no one is listening to you. Okay, so algorithmic bias. Only one example, although we'll mention a couple more later. So this is not coming from data, it's coming from the algorithm. And my best example is very old, but it's still my best example. So let's say you have a site like Flickr, where you can upload pictures, put some tags, and then using, let's say, qualitative filtering, tag concurrence, you suggest tags to the people. So here I upload a picture of London, and I get all these nice tags after putting London Eye and Thames, and then we get all these, and I mark the ones that are good, and I finish. So instead of 2 tags, here I get 8. What's the problem with this? Well, the problem with this is that people will use it. And if people will use it, next time I will put only 1 tag. Now with deep learning, no tags, right? Deep learning can guess all the tags. Well, but the only way the model can improve is with data from people. So if you have a folksonomy, you cannot help people. You need to live with the data from people. So this is like a very slow harakiri, but the algorithm is killing itself because it doesn't get any new data. So don't do this. You can use the suggested tags for search, for other things, but don't help people if you want to improve your model. And then we have bias in the interaction. Let's say you go to this page, it's Amazon.com, so I'm sure you recognize this page. And here there are plenty of biases that you are suffering every day, but maybe you don't know. So the first one is presentation bias. Everything in this page may get a click, everything else doesn't get a click for sure. Do you know how many products Amazon has? It's not the tip of the iceberg. This is the ice cube on top of the tip of the iceberg. Right? It's really huge difference. Then you have position bias, ranking bias. In the Western world, we read from left to right and from top to bottom. So we read here first. And because we believe the ranking of the search engine is good, we will click more on the first result, ranking bias, than in the second one. So that's also related to position. It's a particular case of position bias. You have social bias. For example, when you want to put a review, maybe other reviews will affect your judgment, and then your review will not be completely independent. And that's the case. And then you have interaction bias. Anything else that in this page you can interact with, maybe there's a bias. And the problem is that it's a cascade of biases. It's not a single one, and it's not easy to abstract. So here is one possibility. All the biases on the left are coming from the data or the algorithm, and all the biases in the right come from you. I will call it self-selection bias. It's your own cognitive bias. For example, if you believe that ranking is important, you will click more in position 1. Some people cannot stop to move the mouse. They read moving the mouse. Some people cannot be without clicking, so they will click faster and look less things. So all these things are composite, and then it's a composition of all these biases. So this makes more difficult to analyze this. There's no research on this. And then you can put all together. You can read my article in Communication with CM last year about all these biases together, and then you get this. So I already talked about the activity bias, data bias. I didn't talk about sampling bias, but that's a problem when you use web data. Algorithmic bias, interaction bias. And then we have what I call the second order bias. So people take whatever is doing with the web, and they put it back in the web in a different way. And there are many ways to do that. The most important two, the first one is personalization. And I hope you know about the filter bubble. This is an old book now. But basically it's what is called the echo chamber. So the people can only get options that depends on the history of the personal data, and of course that's biased to what you know. So it's very hard, for example, for me to present you something new if I don't know that you will like it. And if that's not clear, maybe if you saw this movie, that's very clear. So this person was very happy until it found out that it was living in a bubble. And it doesn't matter if the bubble outside is awful, people want to know what is outside their own world. There are solutions to this. So for example, recommender systems are using things like diversity, novelty, even serendipity, but it's a fourth option that I haven't seen I would like to have. It's what I will call my dark side. I want to know what people that is completely different from me is getting recommended. Let's say you have a news recommender. Maybe you get completely weird news, but I want to know that. And I want to know that not because I want to know the news that they are getting. I want to know that to know how far are from me. Because I think today we think they are closer to us than what we think. And I will not talk about that topic. So this is a problem in the cold start because we need the tension between explore and exploit. And I'm doing research on this. And recently, I saw the first paper that looks at this tension between explore and exploit. And it's a paper that appeared in one of the main AI conferences. And this is about echo chambers in recommender system. It's an analytical model. It's not a real system, but the analytical model is quite realistic. And then you get these bubbles. And if you know a little bit about explore and exploit, Thompson sampling, UCB are the classical exploration algorithms. Random will be completely random, which is not very good. But here, for example, is how fast you get to the bubble. Higher, bigger the bubble. Lower, no bubble. So random, no bubble. But of course, the system may go bankrupt because it doesn't sell anything, it's random. So there's a tension between user experience and revenue here. And it's a very complicated tension for all the big internet companies. And each one has a different solution here. But clearly, more random, better for the user, not for the system. And this is interesting because the real echo chamber is not only of the people, it's the echo chamber of the system. So you can think that every system is in the echo chamber of all their users. And that could be dangerous because basically they are living in their own world. Every time you suggest something to for people to click, you are creating the future. So you are building the future. So the system is building the future. And this has not been really researched until now. And I work with 2 master students in our system trying to find how bad is this. Okay, and the second example of second-order bias is not when you have the relevance feedback loop of personalization, but you have real content. And I will show this with an example of the web. This was another of my PhD students 10 years ago. Let's say you are writing a blog page, and you look at the top pages of a search engine, and you select content from these 3 pages that you like it. They suffer ranking bias, but that's not the problem. Let's say they are random pages. Then you put this content in the new blog. Of course, you are not doing plagiarism. You are doing research. So you put quotes, you put the citation to the author, and you put the link back to the source. That's the only difference between plagiarism and research, these 3 things. But you feel a bit of shame, right? There's nothing yours. So you think a little bit and write something that will make this thing coherent. And then after feeling shame, you feel proud, and you put your name. And then you publish this back in the web. Well, in this paper of the genealogical trees of the web, we show that the semantic redundancy grows to more than 30%. And this was 10 years ago. Today, maybe even worse. So who knows how much the content of the web depends on the ranking function of the search engine. So basically, there's a bias to the ranking function, not to the ranking position, to the ranking function. Because this content is what this search engine thinks is good, not what you think is good. And this something happens every day. Next challenge, sparsity. I'm sure you have seen this long tail distribution, but I want to use it in a different way here. It's not the long tail of users, for example, it's the long tail of data. So this is the amount of data. These are all the companies or institutions in the world. And of course, these are all the ones that have big data. So all internet companies, multinationals, and so on, big national companies. However, what about the rest? Well, the rest is a long, long, long tail of all the small stores in the world, and they have small data. They don't have big data. And they will never have big data. And if you know a little bit about power laws, the area under this curve could be as big or even bigger than this one. So there's more data here than here, because the long tail is really, really long. So small data is the problem, and we are not looking at it. I wrote this in a blog in KDD Nuggets, and was the most read blog on that week. And why is the problem? Well, there are many reasons why small data is important. I will not read all of this, but for example, you take the decision with small data, not with big data. Big data is about people. It's about your data. We can understand small data, not big data. And a very interesting book, most innovations are triggered by small data, so this is the small data book of Martin Lidstrom. So we should do more research in big data. Here I have a comparison of different dimensions between small data and big data. Here are the 4 of the 5 V's that I looked before: volume, velocity, variety, and value. But there are other things that are important. Privacy, I will talk about that in a minute. Things like density, identity, relations, flexibility. So there are more dimensions, and in some cases, for example, small data will be more dense, more precise, more strong, and higher. Let me give you an example, and this is related to the work on dyslexia that we have been doing with 2 different PhD students, first Luz Reyo and then now Maria Rochenberger. And this is an example where we need to deal with small data. It's not easy to find children with dyslexia and then do this test. And here I have two results on a recent paper on using machine learning to predict that a child has dyslexia. And here you can see in Spanish much more data, 4,000 children, 4,000 people, English 1,500, and then accuracy 81%, 90%, depending on the language. Here, why is this important? Because even if the accuracy is not high, 80%, the cost of a false negative, basically a child that is never diagnosed with dyslexia and has to suffer all school without knowing what's the problem, is much higher than, say, telling someone that doesn't have dyslexia to go to the doctor and then be very happy after seeing the doctor that they don't have dyslexia. So completely different. Maybe it's more costly, but the result as overall as a society is much worse. Any questions here? No one will ask why the accuracy is lower even if you have more data.
But why didn't they train the same model on 1,500 Spanish children to see whether because that could due to the language. English has a different structure, so
Exactly, that's why I wanted the question, because the difference is that for people with dyslexia, Spanish is much harder because it's phonetic than English. So it's harder to basically to detect it because of that. People use phonetics to help them to find the right words, which is not true in English, and that's why it's easier. So in many senses, English is more difficult, but for detecting people with dyslexia, it's easier. So that depends on the language. Now with Maria, we're working, and she already has some results, in doing it before the children learn how to read and write. So for that, we use drawings and music. So, and that will be really a huge impact, because then children will be intervene when they start to read and write, which is not what happens today. Maybe all the interventions are too late. Okay, privacy, the last challenge. I guess most of you know about k-anonymity, how we can hide some individuals in the group. And all this was fine until a bit more than 10 years ago, when happened the AOL incident. So one set was released to everyone that was anonymized, but just looking at the queries, some people were able to identify one of the users, so this woman. That was the anonymous number of that woman in the data set. And in this case, they went to her house, asked them if those were her queries, and she said yes, and she got a nice pop picture in the first page of New York Times, which was a big problem of AOL, but luckily she didn't sue them, because that was illegal to identify one of the customers. The same happened a couple of years later, 4 years later. I don't know if you remember the Netflix contest. So some people from UT, University of Texas, were able to basically found the sexual preference of one of the users that had a public profile in IMDb, and that was a real legal problem, and at the end they settled outside court, but of course Netflix killed the contest. And after that, in Yahoo Labs, we did some research on how real was this problem, because most of the people thought before that it was very hard to identify a person in millions. But for example, predicting the gender, 84%, predicting the age, plus minus 10, 79%, just looking at a few queries from each person. Even location, so we can distinguish location, age, and gender very quickly, just looking at a few queries. So how many people here never search his or her name in the web? Okay, that's fine. Only have found 2 people that said that in like a few thousand people I asked this question. And one, I think, was lying. And the other one was a very interesting conversation. So that's normal. So this is vanity. So partial name, 9%, complete name, 1%. So if you are searching your name, don't ask for privacy, okay? But next time you feel this vanity urge, ask a friend to search for your name. And then you mix the data, and really you cannot be predicted. And of course, in that case, you have to search for her name or whatever. But at least you mix the data. So let's go to justice. Let's see what has been done in justice in this problem. So maybe the most famous case is the Compas case. It is a software for criminal profiling. So basically, it's a software that will tell if you will commit a crime again or not. And in 2016, ProPublica, NGO, found that was a 2-to-1 racial bias. So basically, if you are black, probably the score you will get will be double of a white person. And also, there was discrimination on poor people, and that even went to Supreme Court between a person and the state of Georgia, because the person was discriminated for being poor. And even there are some inconsistency in predictions. This was found in a case in Wisconsin. So the question is this correct? Is this ethical? I will get back to this. But I'm sure you have seen this movie. So this is another crime prediction. And one of the companies that is behind this is called Palantir. And they are doing criminal profiling even before in jail, because Compas was used basically to say if a person could go out of prison before the sentence ends or not. In this case, it was even before. And interesting, in the places that this has been used, has been hidden. So for example, in Los Angeles, to make sure that no one knew, the police foundation bought the software, not the city. Because if the city buys the software, then it's public. In New York, the mayor decided to buy it, but was never approved by the council, so they never knew. In New Orleans, it was a secret until 2014. I found the news saying that they're using it in Denmark. Last 2 years, I hope it's not true. But what is the main problem? Maybe this works for most cases. But if you do one mistake, that person will suffer forever. Basically, you are going to prison because I think you will do a crime. Like the movie. In the case of Chicago, the same has been done by the city with the Illinois Institute of Technology. That's a different criminal profiler. And here I show one of the main problems of this software, is that basically there's a geographic sampling bias because the police goes to the places where they think there are more crime. And of course, you seek more crime there, right? So it's a fulfilled prediction. And maybe there's more crime elsewhere, but no one knows, and not all of them are recorded because many people decide not to put a filing for all crimes. And this has been proven to be the case. A long time ago, someone wrote an expert system for this, so this was really before machine learning. But they did the experiment to show if the judges were basically influenced or not by these systems, and they found that the answer was yes. So this was more than 40 years ago, that basically judges would believe in the system and would act accordingly. So there was a bias just in using the system. Here I have other applications. For example, people that have tried to predict domestic violence. The algorithm is better than the judge. For example, predicting asylum. So basically predicting if the asylum will be obtained or not, something that's happening every day in the border of Mexico and the US. And the best they got was 82% accuracy. But here what was interesting is that only 1/3 of the features are about the case. All the other features are not about the case. So it seems that asylum has to do with other things like race and so on, and I guess we already know that. For example, appeals consensus, they were not able to predict very well this, but what was interesting in the prediction is that, again, only 50% depends on the case, and 50% depends on the person. So there you have gender, race, and so on. And the most interesting was in this sentence prediction that they got almost 70% accuracy to predict if the judge will find a person guilty or not. And they added, after doing the standard textual predictor, so basically using all the documents from the case, they added images. Well, when they added all the images they had from the case, the accuracy improved in almost 2%. And then they said, okay, let's add also the audio, because they record the trial. And with the audio, they got only 2% more. And the best here is the title of the paper, because they said, we knew the justice was blind, but perhaps it's also deaf. Because it doesn't matter if you add images and audio, the accuracy doesn't improve much. So again, maybe the results are not based on the case itself. So let me go to the final example in detail, because I think this is one of the best examples and shows some of the problems here. So this is about bails in New York. In New York, the bail law says that you should not get bail if the judge thinks that you are not coming back to the trial. So basically, you will not appear in front of the judge. The judge doesn't have to predict if you will commit a crime or not, so which is a bit strange, but in New York, it's only about coming back. So this is the case. So they get bail and pays. Then the only question important in New York is, will appear in court or not? In many other places, the question will be, will that person get do another crime or not? Well, of course, if you cannot pay, you go to jail. However, in the US, there is a special person that will give you a loan that is always there, and they will have to predict if you will come back, because then they don't get the money back, right? So it's interesting that some people are better predictors than the judge. And of course, if the answer is no, you go to jail. So one problem here is that we don't know what would happen if that person had bail. Maybe he would have come back to court and will be a nice person because he was innocent and so on. So this is one of the problems that we have in many cases with data. We need to impute data because we know half of the history. We don't know the whole history. So what are the results here? So they analyzed more than 750,000 cases from New York, and they found out that if you had a model, they could decrease criminal rate in almost 25%, sending the same amount of people to prison, or they could decrease the amount of people in prison by more than 40%, but keeping the same criminal rate. And one of the things they found is that if the model is correct, judges bailed almost half of the 1% that was the most dangerous people. Basically, 56% will not appear, and 62% will reoffend. And this is a paper that was published last year. You can go and it's available. And the interesting thing is that this was asked by the Economy Research Office of the US, not the Justice Research Office of the US. Why? Because prisons are very expensive in the US, so they want to decrease the number of people in prison. So how they did it? Well, they split the set in basically 4 parts. One holdout to do the evaluation, one big one to do the imputation, so basically to predict things that we don't know if will happen or not. I will explain how they did that in the next slide. A training set, and also one that was completely untouched, for example, to other people check how good they were the results. What they use a kind of decision tree, allow some explanation. They use 18 features. Of course, the only demographic feature is age, nothing else. But of course, things like race and gender are implicit here. I mean, all people know that, for example, young man is the most probable person if you get to this stage. And what is the difference? So this is the difference between the crime rate and the release rate. And this is the curve of the algorithm. This is the model. And this is the point where the data is, the judges. And then you can choose any point here. The ones I mentioned at the beginning are this one and this one, but you can choose any point in this curve, which is better than the judge. And another way to see that is here, is that if they are the people released, and these are the people that go to prison, for example, the algorithm will choose people from the most dangerous. And this is what the judges choose. They choose people from everywhere. And here are all the mistakes. And of course, the main mistakes here, because here they leave free almost half of the people. So basically, it's like almost random for the judges. And how they did that and the imputation, well, they divided the judges in 5 groups, from the most lenient judges to the most hard judges. And with the lenient judges, they were able to basically predict the hard judges. So what else? Well, what else is that this algorithm was racist because the data had racism. So this is the data for the judges. So here you have the percentage of black and Hispanic. You can see that most of the people is black or Hispanic if it goes to see a judge. And this is the real number in the population. So basically in New York, 18% are black, 13% are Hispanic. And if you sum both of them, it's 32%. So what about the algorithm? Well, the algorithm was more racist than the judges, but didn't do any mistakes. And that's the advantage. So if you match the judge on race, it still was almost the same. So you see that you could decrease the criminality rate by almost the same. If we take the less racist judge, then still you could decrease the criminality by more than 20%. So the advantage here is that in some sense it's like deterministic. If they see the same kind of prisoner, they always do the same. That's not true for judges, sadly. And there where racism comes too. Questions? Okay, so let me have a last 5-7 minutes for what are the problems that we have to solve as a society. So the question is, can we have ethical algorithms? And if so, who will design those ethical algorithms? Who will define what is ethical? There's nothing written about that. And I'm sure you have read all the cases about how different cultures will decide who should die, depending on which situation. Soon, a whole book about this is coming to print. Basically, what people think about automatic decisions, and also how these decisions change from culture to culture. So in 2017, the ACM did a statement about the 7 properties that all algorithms should fulfill. I will not read the properties, but you can see things like accountability, explanation, auditability, and the truth that today, no algorithm fulfills these things. Now, an algorithm doesn't have to be perfect. The algorithm has just to be better than us. So I think some people ask for perfection when, like in the case of the judges, having the algorithm as a judge is already a big improvement in justice because at least all people is treated equally fair, even with racism. And here we have problems like GDPR or the new copyright directive that makes this more complicated. If you have read the article 22 of GDPR about automatic decision making. That would be a different talk, but that I think that's very important and it's affecting this topic. So things that we typically do that we should not do, I will not read this, but for example, things very important, companies aggressively resist review whenever some people want to basically audit their techniques, like in all this justice software. Or, for example, failing to measure the impact of the deployed system. So there are so many bad practices that we could avoid. Well, if sometimes bad practices are not bad, so this was a joke that was viral a few months ago. So here they were lucky that all the data was about middle age or earlier. But there are some problems that are much harder to learn. So I think intelligence is not about learning, but it's also about forgetting. And in another talk, I like to use this picture. So who knows what animal is that? A cat. Most people will recognize that as a cat. You know, some people take cats even from below the glass table. That's the case. And for example, if you need to explain to someone that that's a cat, you cannot say it has pointing ears because there are no ears. You cannot say many things that you will say about the cat, but you can recognize about the cat. And I always remember this amazing story from Borges, Funes de Memorios, where was a person that couldn't forget anything. So if you had the stupid idea of asking him how was his morning, he would take like 4 hours to tell you how was the morning. So no one would talk to him. And the other problem that's very hard is that something that I think many people always forget is that you cannot learn what's not in the data. So for example, if you have 1 million pictures of cats and there's no such picture like this one, you will never be able to predict this one. Also, there's another thing related to this is that I don't know why, when we do all these models, we don't have a class that is I don't know. We have a hard time saying I don't know too, but I think computers should say I don't know because the probability is only 20%, so maybe I'm wrong, right? Maybe it will be the most popular class, but it will be more honest. So some recommendations. So design for people, respect for the limitations of our systems. Remember that learning from the past doesn't mean to reproduce it. Ethics, explainability, more evaluation. One that really is important. Don't use human in the loop. If we're in the loop, we're not in control. And then they're the masters, not us. We are in control all the time, from the design to the operation to the usage of systems. So the machine is in the loop, and the humans are in control. And of course, we need to study more intelligence and consciousness. I'm sure people from cognitive science will agree on this. So the future. This is my real worry today. After every election, I'm worried about this. Why? Because then we may have this. Proof you're not a human. There are no more humans. Correct. Ha. And there are no more humans not because the robots kill the humans, because the humans kill themselves, right? So, and if you, I recently read the last book of Harari. You know, have read it, 21 Problems for the 21st century. And he's really negative. And he said that humans can be hacked. And then I'm trying to be positive. They say that everyone in the Silicon Valley is positive. So I think I cannot be hacked. Or at least I believe that. So I was recently in an interview that he did in Stanford like 1 month ago. And he said something very, I like a lot, and I think many people have said, but the way he said it was that the easiest people to manipulate is the people that think that cannot be manipulated. And every day I see that. So this is related to the work of Lisa Feldman Barrett about emotions are predictions. So she said that our brain is like a machine learning algorithm. And if that's true, what is important is we can change it. So we can change our model. So next time that we do something we don't like, change your model. You need to train it. That means that you need to think, stop whatever you do, and do something else. But you can do it. And I have tried that, and it works. Maybe it's related to meditation. I don't know, but I don't do meditation, although he has a chapter on that at the end. So things like loss of jobs. But I think we can leverage AI, and we can do things that we are good at. Why not doing more literature and art? Loss of skills. So how many people cannot find a place without the GPS today? We are losing our hunting skills. Well, maybe okay when they're better than humans. But remember, if you have no battery, you need those skills. I practice them. I don't use the GPS. So there are things that are much harder to refute. For example, it's true that this will be a network of machines. We are not really a network. That changes a lot. So he says, even more inequality, no sense of purpose, and irrelevance. Well, that's what he thinks. So the epilogue. We need more transparent algorithms. This will be my worst nightmare, that if we don't worry about how an algorithm should be ethical, lawyers will, and then we will have to pay insurance. For example, insurance for the people that train the data, for the train the model, label the data, program the model, and so on, for everything. Harari believes in augmented humanity. I don't know. But I think he has strong points, and we need to try to refute them with actions. Still, I'm positive. I think we can do AI for good. I was just 1 week ago in Geneva in the conference of AI for good, and there are a lot of people trying to use this for other goals. But when you see things like usage of Facebook in Philippines, social credit score in China, or use of WhatsApp in Brazil, you get scared. So anyone read this book, The Naked Sun? Yes. So a very nice novel by Asimov. It's a detective novel in the future. And what I will use is not the plot, but in that world, every person lives in their own territory without seeing any other human. So it was like, we live alone and we interact only with machines. I hope that's not the case. I like to be with people. But in that case, if you saw the movie Arrival, that will be my desire. We need nice aliens to come soon and to make us talk to each other. Thank you.
Thank you, Ricardo, for this wide exposition and raising so many questions about our future and our duties and what can we do. I'm sure some members of the audience have questions for Ricardo.
Hi, thank you for the talk. I was curious about how do you give some a priori to the model to be less racist. I was thinking about having some loss function with some weights, lowering the racism of your model, but then also keeping the accuracy. But I don't know if you have.
That's a very good question. I haven't worked on that, but I have read a few papers about that. I think there are at least two important issues there. The first is that It's true that more, say, Black and Hispanic will commit crime in New York, and this is because of historical reasons, like poverty, discrimination, and so on. So the question will be, is there a right percentage to put of racism to have the right model? Very hard question, very hard ethical question. And there's a very interesting paper on that, because one other thing that is important is that even if you have the right algorithm, that algorithm will sanitize the system and will make it much difficult to improve the system. So it's basically, oh, we have something is working, not touch it. So one problem with this use of this algorithm is that basically society doesn't evolve, because you keep, for example, some racism in the problem. And the second one is that there have been many recent papers is that there's no agreement on what it means to be fair. So, and there are papers that show that most of the measures that, for example, what you said, that seem very reasonable, they don't work. And I can point you to a paper that basically shows that all the fairness measures that people are using, they have a problem. So there's no single fairness measure that works all the time. And one reason is that, for example, even if we use a group fairness, like with fairness as a society, of course there will be some individuals that will suffer unfairness, and vice versa. So that's one problem in general.
Thank you.
I think we are recording.
I want to record you.
Yeah, maybe some more details. When you were talking about explorer and exploitation, you were mentioning this AAAI paper. I didn't quite understand. So to me, the optimal algorithm was the one performing worst. So what was the notion of optimality in there?
That's a good point. So the option of the optimality, for the paper, they were trying to see, for example, the typical option of optimality will be revenue. And basically revenue, the best local optima will be to keep you in your bubble, because that works. But they don't know if in the long term there's another point where it could be better. And that's something I'm looking at. So basically, if you do local optimization, there will be local revenue that basically is create the bubbles. And of course, random will be the worst in that case. So there's a tension between user experience and basically the goal of the company. But in every company, the optimization function will be different. They use a simple optimization function, which is realistic. Like, for example, one would be click-through rate. So you can try to optimize click-through rate. And of course, if you put random, that will be bad. But if you put something that's not random, it will be better. But of course, you will create the bubbles because you are using what that people like. So it's a very interesting paper. It's the first one I see in that topic, which I think is a very important topic. Yes?
When you look at decision making, actually when you look at humans, there's like two ways of decision making, like fast and slow, as they say. And especially when you look in the medical literature, what you see is that medical errors are often made by fast, which is like pattern recognition in some ways. That you say, like, I have the data, I immediately detect a pattern, and that's a decision I make. Where obviously your bias will be very important, and obviously you miss a lot of outliers. While in the other way of slow is like you do like reasoning. You have to do explicit reasoning, which theoretically might be better in some ways. How do you see that also in the algorithms? Because depending on the type of algorithm, you will explicitly use one of these types of reasoning in some ways. And which do you think might be better in some applications or not?
Yeah, that's a very good question. So I think the application depends a lot. For example, let's say today air control in airports, you need to decide fast. And today the automated algorithms are much better than people. So people are just there to supervise that everything's going well, and to do something if something really completely unusual happens. So in that case, I would say, if it's online, we need to use a fast algorithm. When is better than people? In the case where your decision will affect the life of a person, I think we need to go to the other side. And I believe what is missing today is to really add more semantics to the models. I think the best combination of deep learning will be deep learning where we have more semantics of the problem encoded in the network. And I don't see that yet. Or for example, could be, let's say we have a set of rules. Let's imagine we have agreed a set of rules. It's very different that we predict which rule to use rather than which low-level feature we need to use. If we had, for example, some solution. So I think it would be better to mix the best of, say, reasoning to the best of deep learning. But many people is using deep learning just as a black box. So they're not thinking much. Even, I don't know if you have seen all these examples on changing even one pixel in an image, and then you change the label of the image, which you think after that is what the model is learning, right? Not sure if it's learning the right thing. It just works.
Hi, I have a question about transparency of algorithms that you talked about before. And yeah, my question is, I kind of get confused when I think about transparent algorithms here, because once the algorithm is transparent, it's out in society. So now people know how it's working, and they might start behaving in very weird ways, like as when you examine someone, they are going to start like trying to trick the system and behave in that way. And yeah, follow-up question, building up on this is, with this justice framework in which you want to predict someone that is going to commit a crime to jail it beforehand, maybe, again, once the system is out, it can just tell someone, hey, I'm going to jail you, and that people with this new information just won't commit that crime. So maybe here, I think that sometimes we have a very static vision, and the system should be constantly in interaction, and having this in mind, like playing chess with society. So yeah, what can you say about that?
Yeah, so let me start with the second question, which is easier. Yes, these systems should be dynamic. But it's also related to the first question. I think when we say, for example, how much the public should know, maybe we don't need everyone to know, but we need some group to know, and then to make sure that the system is doing the right thing. So for example, I think it's different to be transparent with the user of the system, like for example, transparent with the judge, to be transparent for everyone. Because then a person may game the system, so may act differently to game the system. So I think transparency also, we need to talk to transparent to whom? Not only to everyone, but maybe for, let's say, for a committee of judges or whatever that is using the system.
No more questions? Okay, so thank you very much.
Thank you.
Ricardo.